Thanks for the introduction, and thanks to Christine and Dave for organizing this great conference. Today, I'd like to tell you about some recent results that my group has produced on experimentally controlling QuDits with 10 or 20 or more states in them. And before we get started on the technical part of the program, I wanted to just briefly mention that the research philosophy we use, this is going to look very familiar to many experimentalists, but we are really a tool development group. We are looking at building and verifying and understanding limitations of new experimental tools that can be turned to multiple different purposes. And so I occasionally get somebody who's kind of going nuts during a talk like, oh, but what's the application you really care about? Or what's the principle you really want to measure? And that's not really the point of what we do. For us, having these tools available and understanding their limitations is a goal in and of itself. Specifically with regards to getting into the direction of QuDits, what motivates me the most about this is actually coming from the fact that we've worked for many years on building these different quantum processors here at IQC. We have 4 different processors. I'm involved with the development of 3 of them. And when we look at the kind of work that it takes to build these, forget about QuDits for a second, just think about qubits. Already there is a lot of engineering, a lot of technical work that goes into these, and any kind of improvement on the power of these processors is a very difficult thing to achieve, because we usually are going to need to take multiple of these different instrumentation subsystems and either troubleshoot them to reduce errors or redesign them to accommodate more qubits or something like this. It takes a lot of effort, right? And the thing that seems a little silly about this is if you take one of these ions that we would use to encode a qubit, you zoom in on it a little bit, you say, well, look, this is not a 2-state system. We have enormous amounts of quantum resource just sitting on the table waiting for us to use. I know I don't need to sell all of you on this idea, but really we're pushing on, can we use a really large fraction of that Hilbert space? Now, in my first slide, I said that I wanted to have some kind of concrete applications, and the applications that I hear about for these qudits are basically the same ones that you've all been hearing about for the entire workshop, right? So there are a lot of different potential directions we can take these tools. We can look at simply data compression type applications. We can do all sorts of different quantum simulations, would be potentially aided or enhanced by the use of multiple different states. And you've heard some really great talks already about modeling AKLT phases or studying quantum chemistry or studying lattice gauge theories. I will not have anything more insightful to say than those experts. I'm here to learn from them. Same with the quantum error correction and all of these different things. But the point that to me is important is that we do have a good prospects for studying all sorts of different things if we can get these multi-level qudit controls in hand. And it turns out that actually this is not so difficult. So this work from Martin Ringbauer has been really beautiful in terms of showing that we can take these trapped ion processors. We don't really need to change them very much. We can take the same exact trapping and cooling techniques that we've always known. We can use the same principles for implementing entangling operations. We add a few extra frequencies on one of our lasers, and we have a universal quantum processor. And this is amazing. This is a really cool result. And we were very excited to see this a couple of years ago. So the natural question that occurred to us was, if we know that they can implement universal qudit quantum processing, what's the limit on how many states we can add in? Can we make them even more powerful by adding more and more and more states? And actually, limited Hilbert space compared to some of the ions that we can work with in our lab. Now, when I said that, I was thinking that, we had some throwaway comments to a paper introduction or something. I thought we were a long way from going to Hilbert spaces larger than 7 or 8 states. But within the next couple of days or weeks or something, my students came back to the lab meeting saying, all right, so we spun up barium-137, we can trap it, we're doing spectroscopy, and how many states did you think we would need to set some kind of a record? And so off we went to the races, which was really interesting to see. And the key point here is that we have an atom with a larger nuclear spin, we have a lot of different states that we can make use of. And in barium-137, which is the ion I'll tell you about today, we can go up to 25 different states that we can distinguish in what I call a single-shot measurement. It's a multiple-step process, but in a single experiment, we can do this. Even more states are available if you don't mind that some of them will be indistinguishable. And even just looking at the Hilbert space scaling, the amount of additional complexity that you can pack into one of these massive multi-level QuDits is just enormously better than what you can do with qubits. And so we think that this is potentially a really interesting direction for exploring the trade space. How do we make these processors more powerful, right? All right. Now, in the level structure of barium-137, this is basically what we've spent a lot of our time thinking about, right? If we look at this ground orbital, there are 8 different states accounting for all the hyperfine structures, even sublevels. Initially, I was thinking this is sort of what we would work on. But up here, if you look at this metastable orbital, we have a whole 24 states that live not forever, but basically forever compared to most of our experimental time scales. So we might as well treat these as ground states, and we might as well treat these as qudit states. So in this experimental setup, there's multiple different ways that you can drive transitions between different states. You can have microwave transitions working between states in the same manifold. You can have optical transitions across different manifolds. And for today, I'm really going to focus on our optical quadrupole transitions, but there's even an additional layer of complexity that we can add if we want to add more controls later on. And so we needed to go from this sort of basic atomic theory that we knew something about the energy states of these systems, and we needed to find all these transitions, get coherent control over all of them, and that took a little bit of time, which I'd like to walk you through some of the challenges that we dealt with. Over here on the left, I've shown you the energy eigenvalues for the D5 house manifold that we'll be using, and you'll notice that I've got 2 different colors in this bottom set of lines here, and that's telling you that we have 2 different angular momenta getting mixed together here. So even just calculating these things is just, it's minorly annoying because we have to deal with this more complicated Hamiltonian and diagonalize it for the energies, which the energies aren't so bad, but the transition strengths are really a little bit annoying, especially because we're not able to assume that our energy eigenstates are eigenstates of the angular momentum, so they kind of mix together, and it's like kind of annoying to predict the transition strengths. Okay, but we got a handle on all of that. We're able to match our oscillator strengths with our calculations quite well. There's a little bit of deviations when you account for ellipticity of the polarization isn't in our model and things like that. But we can really figure out what's going on inside this atom. So great, step 1 done. The next question that you run into is, which transitions do we want to use for encoding our qudit? I'm focusing on that question because we usually think about choosing states, right? We look at experimental system, and we say, what are the stable states? Which ones do we want to use for our qubit? But if you think about it, really what we're looking at is how well behaved is the transition between them, and how well can we control the transition between the two states. In the QuDits, the generalization of this principle is, let's say, less obvious than I might have liked to start off with. If you have a qubit, you have exactly one transition that you need to pick out. For qtrits, you need 2 or 3. For qquarts, you maybe need up to 6. We've got 80 different transitions running around here. It wasn't entirely obvious which ones were going to be most useful for us. And to be honest, it's still not 100% clear which ones are most useful, but we've learned a lot of interesting lessons. So what I've depicted here is that a lot of these different transitions are allowed by quadrupole selection rules. A lot of them aren't. It's kind of a bit of a mess. So one of the things that we first started looking at is the magnetic field sensitivity and the oscillator strength, or the transition matrix element, were the two factors that seemed to be most important for understanding the fidelities of our operations. And so we did a little bit of, borrowed some signal processing theory, and found that you can, this is a technique where you can basically construct what's called a filter that tells you about the spectral response of your quantum operation, and then if you model the magnetic field noise or the detuning noise of your system, then you can get some analytic approximations to what the error rates ought to be. And we found that we get a product of the square of these two different parameters that we told you about in a slide ago. We matched this up with the data, and it seems to be a pretty good fit for the noise environment in our system. And this is going to be important because today I'm not going to talk very much about optimizing gates or anything, but we need to start developing figures of merit. We need to start understanding what are the sort of key parameters that will affect the fidelity of our operations. So this was one of the tools that I was particularly pleased with. If we take that result and map out what that parameter would look like for all of these different transitions, I'm giving you now a transition matrix from my ground states. Those are on the horizontal axis, to my metastable states, which are on the vertical axis. You see that, there's some patterns here. There's a clock qubit that's really, really, really good. There's an almost forbidden transition that's really, really bad. Putting all these together, again, is not, you can squint at this a lot, and we do. We have various tables like this plastered all over the walls of the offices, but it's not entirely obvious how to select these things. So far, what we've been able to do is we can predict our Rabi flopping errors quite well using this heuristic that I showed you on the previous slide, as long as our transitions are well separated in frequency space. We do find that some transitions are not well separated, particularly motional sideband transitions from some states will sometimes overlap in frequency with other transitions, and this causes some problems for us, so we try to avoid these as much as possible. It's not entirely clear what would be the optimal set of transitions to use for any of these operations, but we've found some that work well enough for us in our state preparation and measurement, which is the main thing that I'll talk about today. But there's some interesting open questions here, right? There's this optimization question. There's some questions about how do we calibrate these things. Do I want to go and measure 80 frequencies every day? Not so much. That sounds terrible. And so I think there's a lot of interesting research to be done just in terms of, like, we have this massive and really complicated resource on our hands that we still just don't even understand what are the best ways to possibly control it. What I'll be showing you is a good way to control it, probably not the best. Okay, so then the last piece that we looked into before starting to implement our quantum information operations was this calibration problem, because we really, really don't want to be making 160 calibration measurements every day. And fortunately for us, there's really only two main experimental sources of drift in the transition frequencies. These come from basically the reference cavity of our laser and the uncontrolled magnetic field drifts. And if we probe two of our transitions, the one that's least sensitive and the one that's most sensitive, we found that we can really predict quite well where all of the other frequencies will be to within several hundred hertz. And so this is the procedure that we use now. We do our calibrations with two frequencies, 5 pi times, and we can work with maybe 38 or so transitions every day, and it works well, reasonably well. Please excuse me rushing through my talk here. I'm hopped up on about 20 doses of asthma inhaler, and so I'm probably going faster than I meant to go. So interrupt me if you have any questions. Yes?
It says calibrate pi times.
Yeah.
Pi is irrational. So how many times do you calibrate? I don't understand.
My apologies. Pi times here is experimental jargon for the Rabi frequency. So we are calibrating how long of a duration do we need to apply the laser to induce a pi rotation on the qubit block sphere, let's say, or to transfer the maximal amount of population from one state to another. Okay, so we've got all this really well dealt with, and I showed you a few of the sort of calibration plots earlier, but it's kind of impressive having gone from we had some really messy looking plots initially to now these guys have 38 different Rabi flopping plots with beautiful coherent oscillations all over the screen, and so that's been really fun. The next challenge that we ran into then is sort of how do we initialize to some state in this manifold? Because there's a lot of them, and you can't use the same procedure for all of them. And so what we're doing now is we started off by saying, let's look at this manifold, the f equals 2 states, I'll call them, in the ground manifold here. And let's try to prepare arbitrary sublevels in this manifold. The way that we're doing this is a narrowband assisted optical pumping technique, which is a somewhat new-ish thing that's been coming into the mainstream. And the idea is as follows. We take a laser that cleans out the f equal 1 states. And then we have 5 states left here, and we only want 1. So we take laser frequencies that clean out 4 of those states, in this case, by driving them up to our metastable manifold and repumping them. And if you do this enough times, then you will eventually push all of the population, or almost all, into the one state that you care about. So this is what we're doing for the first step of our initialization process. This is the first place we really ran into some big issues with running into spectral crowding and having to switch around which frequencies we were using and stuff. But eventually, we were able to pick out the right transition paths that would allow us to prepare all of these 5 states with some close to 99% probability, which was good enough for our purposes at the time. Sorry. Okay, so that gives us 5 states, right? That's not as many as I was promising earlier. And what we're doing to prepare the states in this larger manifold is basically we just take that same procedure and add a pulse up into the metastable state. What we've taken to doing since DayMop is, in addition to applying all of these different laser pulses to prepare the state, we add a measurement right after we do the preparation. And what that does is, if our preparation step fails, then pretty much all of the ways that it fails will leave some population down here in the S manifold where we didn't want it. So if we measure the system and we see that, in fact, we have population left in the S manifold, we know this is a failed run and we can throw it out. Doesn't matter what other computations we're doing, we can get rid of it, which is nice because that means we can kind of by sacrificing a few bad experiments, we can push our precision much higher. Now, it doesn't make sense to prepare a whole bunch of states if you don't have a way of convincing yourself that you're measuring what you wanted to see. So we needed to use a similar readout procedure that I think you've seen in other talks so far. So we're going to run our diagnostics by probing one state at a time. We bring down another state. We check it again. We bring down another state. We check it again. We're going to attribute the first location or the first time that we see fluorescence as telling us the state in which the qudit resided. And we also know that there should always be at least one bright state. So if we see a run where there are no fluorescence counts anywhere, then we know that our measurement failed, and we can discard those results as well. So this is the set of techniques that we put together when we worked towards putting this 25-level qudit online. And what I'm showing you here is our most recent data set on the SPAM results. And what we have is on one axis, the state that we attempted to prepare. On the other axis, the state that we measured the system to be in. What we would ideally have is this sort of like diagonals with ones on them and nothing outside of that space. And for this set of experiments with the transitions that we found and everything, we're able to reach a 99.5% success rate on our state preparation and measurement. We're having to throw away maybe 7% or so of our data runs because of these detectable errors that I mentioned. This is all preliminary data. We think we can probably improve some of these numbers, especially there's a couple of states up here that are particularly problematic when we try to prepare them. We have other data suggesting that if we improve our calibration process, then we'll be able to beat down those errors quite a bit. But what I'd like to highlight is I get asked sometimes how these qudits compare to the equivalent qubits. And as you all know, that's a tricky question to answer in many ways. But if I take a very simple-minded approach of saying, well, I just want to know, like, how does this error rate compare to what error rate I would get for the equivalent number of qubits? If I have 4 qubits, which is not as many states as what I'm showing here, then I would only, even with a 99.9% fidelity, I would only get this same error rate that we're achieving with the larger Hilbert space. So that, I think, is sort of an interesting comparison that our state preparation and measurement, at least, compares well with a 3-9s procedure on a set of qubits. So this has taken us quite a bit of time to spin up. It was sort of our main flagship result until about, 2 weeks ago or something. And of course, one of the obvious questions that I always get, and rightfully so, is, can you prepare superposition states? Are they coherent? Do you have the phase control over all these transitions, right? And what a lot of groups have done, and you saw this in some talks already, is that they will implement quantum gates like you would do in qubits, but the generalized versions of those. And they'll use these randomized benchmarking type of protocols. And the thing about randomized benchmarking protocols is they're great when you have really low errors, like 0.5% error, and you need to amplify that to really understand how big it is. We're not entirely sure we can achieve such low error rates with 25 states at the coherence times we have right now. And so what we're doing is a more simple-minded Ramsey-style measurement. So we're inspired by the T2 measurements that are done in qubit systems. And if you think about how the Ramsey coherence probes work in 2-level systems, first of all, you create an equal superposition of your 2 states. In this case, I'm showing you what 3 states would look like. So that's how we're going to generalize, is like an equal superposition of all 3. Well, equal-ish. We'll deal with that. So we'll take this equal superposition, and then to convince ourselves we have the phase control over all of these different transitions, we will reverse that mapping, and we'll imprint a different phase on each of those transitions and vary that variable phi, and look at how the population in the initial state 0 oscillates. So in a qubit, you would see just oscillations between 0 and 1. When you go to these larger systems, what we see is still, the oscillation patterns are more complicated as you vary these phases, but you do still get recovery, sort of a revival when all of the phases are set to 2 pi, for some definition of 2 pi, which we've had to think about a little bit. And so we were able to demonstrate with these 3-level systems that we can get pretty good recovery. Again, lots of things need to still be calibrated and twiddled here, but the initial results seem quite promising. And we've extended this already to 5 and 9 levels, and you can see that as we go to larger systems, the sort of revival peak gets narrower with this procedure that we're using, but we do still get pretty good recovery of the coherence, and above 75% or something. So, of course, we want to clean this up a bit, but we know how to extend this to the full 25-level Hilbert space on paper, and we're working on implementing those experiments right now. Okay, so that's all the data that I have to present so far. I think the biggest surprise for me in all of this is I have been the pessimist in the group for the last couple of years. We keep saying, I will say, okay, great, go measure where things fall apart, but I'm sure they're going to fall apart before d equals blah. And they're like, yeah, whatever. And they go back to the lab, and they're like, never mind, it doesn't fall apart. Here you go. So we can do really high-fidelity state preparation and measurement with these really large systems. We can control many different transitions. I think that for these large systems, the choice of transitions is sort of the key question or secret sauce that we need to get a better handle on. We're going to be extending this work eventually to try to add Raman transitions, because this will be more convenient for implementing entangling gates. As I mentioned at the beginning of the talk, we have other quantum processors coming online that we hope will also be able to make use of some of these QDIT tools. And of course, I think it's really unclear to me, and I think to most people, what is the optimal number of states to use in your Hilbert space. And maybe it's probably not 2, but maybe it's not as many as 25, and what of those trade-offs is going to need some more careful analysis that's informed by experimental measurements of the error rates with different dimensions. And so that's all I really have to contribute, but Gaurav, Peijang, and Nico are all here at the conference. They took the last set of data that I was showing you. They are the real experts on this work, so talk to them if you'd like to hear about all the nitty-gritty lab details. And thanks to everyone who's contributed to all these experiments. And thank you for your attention.